Welcome, everybody. We're going to be talking about machine learning today. Often people think that data science is mostly about machine learning. And when folks think about getting into data science, they think they're going to be spending all of their time doing exactly what we're going to be doing today. But the truth is that there are other aspects to data science which actually turn out to be even more important. So what we're going to be doing here is just concentrating on one small part of what is usually a large team-based event, right? So for an entire data science project, you'll have many parts. You have to define your problem. You have to work with your stakeholders, with your business folks, with your researchers to define what the problem is. And this is actually a really important thing. It helps you determine whether there's anything to solve in the first place. So you have to do data exploration. And this often requires quite a bit of creativity. And all of this requires a real team approach. Then we start getting into this cycle here where what we're doing is we're taking our data, we do something called feature engineering. We'll talk a little bit more about that. But then we do the machine learning, the deep learning, applying artificial intelligence. That's what this part is right here. And it turns out to be a much smaller part of a much larger project. It is critical. And so it is I was about to say that it's a necessary but not sufficient part of a data science project, but actually I can think of some really good data science projects that had no machine learning. So it's often a very important part of a data science project. It's also really cool. So we're going to be talking about it today. And we're going to be talking just about the modeling part, a little bit about assessment, and we are totally ignoring problem definition. It's being given to us. We're totally ignoring data exploration. We're being given data. We're not doing any feature engineering. We don't have to deploy anything, so we're going to concentrate just on this. That means that we're not going to be following best practices. Normally, when we start a data science project, what is a really good thing to do when you first start a data science project? Anybody remember from way back at the beginning of the summer? It's the first thing you do when you start an analytics or data science project. Data science folks, you can chime in too, because I know you know. Yep. You have to define the problem. That's true. That's true even before you define the problem. Donnie, can you think about what I harp on early on in classes? It's okay if you don't remember. That's okay. No harm, no foul.
You setting up a GitHub repository?
Yes. Yes. No harm, no foul, but if you got it right, you're going to be celebrated. Yes.
Yeah.
So normally what you do is you set up a repository, you define everything, you gather everything together so the team can work together. What we're doing here is we're just setting up pure machine learning software just to go through that cycle. But know that this is not the preferred way to do it, but it's a really good way to learn about what it's like. So I will show you how to do machine learning today. We're going to install all the software. But we need to have an unwritten agreement that if you do a machine learning project, you'll actually create a repo first and go through all the steps. Deal? Thumbs up? All right, do as they say, not as I do. Yeah, that's sorry thing. All right, excellent. Well, let's get started. So we have a problem that we're going to be solving here. And the problem is an interesting one. It's a real world problem and was actually just recently solved with a collaboration with the Data Science Institute and an archaeologist. And we're going to first talk about, we're going to be introducing that in just a moment. But in order to actually do our work, we're going to need to install the software. We're going to need to download our data. Then I'm going to talk about the problem. Then we're going to have a breakout room. I'm going to ask you to think through how you might solve this problem if you didn't have machine learning tools. Because it turns out you can learn a lot about machine learning if you think about human learning. Then we're going to do some actual hands-on machine learning. We're actually going to build some models here. Then we're going to go into breakout rooms again, and we're going to try experimenting with these and see if we can come up with the best performing model. And finally, we're going to end with assessing how well our model works. And that's what we're going to do today. So we're going to start by installing something that's called H2O. And you can get to it just by, and that's a repo, and I'll paste the repo in here again so you can get to it. So here we go. There's a link to the repo. So we're gonna go ahead and go to the H2O website. So here's the H2O website. I actually know the folks at H2O pretty well. I first made contact with them when they actually started up, and they're brilliant folks. And what they've done is they've created a platform for doing machine learning, and it's very, very fast. It's highly scalable, and they spend a lot of it. They spend a lot of attention and care on how to put these algorithms together well. So we're going to be using their open source software to actually solve a problem. And it turns out their software can run in one of many different ways. And one of them is something that's called H2O Flow. And that's what we're going to be using. Let's go through how we download this first. So you go to h2o.ai, and you're going to click here on where it says open source. And then down here, you're going to see where it says download latest. So give me a thumbs up if you're sitting right here. Give me a red X if you need a little bit more guidance. But thumbs up, got some thumbs up, excellent. Red X if you want me to stop. All right, click that. And then this is going to be, and there are instructions also in the repo. But what we're going to do here is we're going to download H2O. It's a zip file. You're going to click on download. And on Windows, you're going to see it's going to be downloading a zip file right down here. It's about 475 megabytes. We don't need to fill this out. So you can just click close on that. So on Windows, it's going to be installing, or it's going to be putting in our download folder. So I'm going to show you how to actually get this installed in Windows, and then Umang is going to show you how you do it on the Mac. So here, it gives you instructions. You're going to pretty much follow the instructions, but not exactly. So we downloaded H2O. On Windows, if you click on this little arrow right here, where it was downloaded, you can say show in folder. Oh, that's actually, let me extend this a little bit. So you click on this and it says show in folder. So we're going to click on that. Give me a thumbs up if we're there. Thumbs up, thumbs up. Give me a red X if you want me to stop. Thumbs up, excellent. Show in folder. And then it gives us our File Explorer. This is called File Explorer in Windows. And you can see actually I've downloaded this a couple of times. So I'm just going to go to this one. This is what I downloaded earlier this morning. And what I'm going to do is I'm going to right click on it. And I'm going to say extract all. So I'm going to go to where it was downloaded. I'm going to right click on it. And I'm going to select extract all. Give me a thumbs up if we're good. Okay, give me red X if you want me to stop. Okay. Extract all. Move this over to where you can see it. And this is kind of a tricky thing. I want it to extract, it already has a subdirectory, so I just want to erase that whole thing. I want to extract to my downloads folder. I just want to extract to my downloads folder. And then I'm going to click extract. It's going to throw an error for me because I've already created this. That's okay. You click extract, and it should it should extract all that for you. And here at the error it says, hey, you've already, well, I'll say replace files at destination. So it'll take a moment. It will extract. Okay, and then we'll open up another window. So go ahead. It's taking a long time. Okay, yeah. Download, we'll give you a moment to complete your download. And then we're going to see if you have Java. And if you don't, then we're going to help you download that as well. But we're planning on, we're taking the time to make sure everyone is on the right page. So no rush. Give me a green check and leave the green check up there when you have downloaded and when you get this window. Okay, green check. Okay, let's go ahead and hop over, Umang, to you. Umang's going to show you how to do this on the Mac. And then by that time, we all ought to be hooked up. So Umang.
All right, give me just 1 second. All right, there we go. Oh, okay. Give me 1 second. This is a new Mac. Need to.
And go ahead and continue putting up a green check if your downloaded has completed in Windows. And Umang, do you need another couple of minutes? Because I can continue on for getting Java as well. I know you're good.
Okay, it's working. Okay, great. Okay, so pretty much a very similar process. You go to H2O's website and go to open source and download latest. And this just downloads to my downloads folder right here, which automatically on Macs uncompresses. So you should get a folder called H2O 3.32.1.4 in your downloads folder straight away, which you can then use the terminal to start up. Jesse, do you want to start with that?
Yeah, go and do that. Go ahead and finish up starting up H2O on the Mac. Since you're here, it's perfect.
Perfect. So then we can open a new terminal and I can go to my downloads.
Can you open the terminal?
So you can either do command space and just type terminal and you should be able to open up a terminal, or you can go into Finder and go to your applications and you should be able to find your terminal under utilities right there. So once you have terminal open, you can CD to your downloads, which just means you're changing your directory to your downloads folder where you have H2O stored. Then I can see what's in my downloads folder and I can see that my H2O folder is right there and I can change
all you had to
directory.
do that then was open terminal, type CD space capital D downloads.
Yep.
And you did ls to list all the files. Okay.
And then once you are there, you can use this command that is also here on the H2O website, java-jar.
So let's pause one more moment if you don't mind. So you
Yep.
did an additional CD
into the H2O folder. Yep.
Okay. So CD H2O-3.32.1.4, and that put you into the subdirectory.
Yep.
And then where did that Java command come from?
So here on the H2O website, they actually have this exact same list of commands. So you basically, again, CD to your downloads. If you're on Windows, you want to unzip it. If you're on Mac, it's already unzipped for you. And then you can change directory to your H2O folder that you just downloaded. And then you can use this java-jar h2o.jar command, and this will start up H2O on your machine. I have it typed up here, and once I do that, it will slowly turn on and we can start using H2O.
So
this takes a second.
An interesting thing that's happening here. It's loading a whole bunch of stuff. Sometimes things will fail, but then it fixes itself. Although maybe it won't recover from this. No, it did. It recovered.
It did. Yep.
So what's happening is that H2O is running in the background as a service. So it's running under Java. So it's a Java program. That's why you had to call Java to run it. And now it's running as a service in the background. And the interesting thing it does is it starts running a web server, which is running just locally on your machine. The whole idea behind H2O is that it's a service that will do machine learning for you, and you can interact with it from R or from Python or interactively from a web browser, and that's what's called H2O Flow. So it actually says, if you look on the bottom of that terminal, it says, open H2O Flow in your web browser, and it gives you the address, http://10.0.0.105:54321. And what that means is this machine using port 54321. And when you do that, what happens when you put that into a browser?
So I can copy it right from the terminal. I can go to Safari or any other browser, paste that in, and we have H2O running on our machine.
So that's on a Mac. Let's do the same thing, but on Windows. All right, great. So we have for our part, we have downloaded, and it looks like everyone has downloaded now, which is great. So now we should be here. It opens up the downloads, and you can see this right here. And we're going to open up our own command window, but we need to figure out exactly where this is, because it can be different places on people's different machines. So if you click on, and there are going to be two different things. One is going to be the zip file. One is that subdirectory.
We can't see your screen.
Oh, thank you very much. Here we go. All right, so we have gone to H2O, we've downloaded, and when we did that, oh, come on, you. It popped up this downloads window when we downloaded it. We're going to right-click on the folder that's H2O-3.32.1.4. That's just the version. Right-click on it and click on Properties. And if you do that, then it will show you the location of where this is. It shows you where your download folder is. So mine is C users Spence JB downloads. So I'm just going to copy that, highlight it, do a Control-C to copy it, and then that's all that I need to do. Now I'm going to go ahead and I'm going to open up my terminal window in Windows. Let me show you what this looks like. So down here, let's see if you right-click on your start, one of the things that you'll get is command prompt. So you right-click on your start, you select command prompt, and then you should get a prompt. It'll appear someplace on your screen. This is what the prompt is. All right, I'm going to go and clear everybody's feedback. If you would please go ahead and give me a green check if you now have a command window here. Give me a green check if you are on Windows and if you are here. Give me a red X if you're on Windows and you're not here. Okay, let's go ahead and let's go ahead and I'm going to set up a quick breakout room to get you caught up. And Preston, if you can help out, Raj and anyone else, I'm going to go ahead and create a breakout room for you real quickly. We're not going to get very far ahead, so don't worry. Breakout rooms, I'm just going to do one breakout room and assign you both real quickly. Preston and Raj. Okay, there you go. And you can hop in and hop out whenever you want. All right. Okay, now. So, oh, you know what's really fun? Okay, now what we're going to do is we're going to do a CD space, just like the commands before, CD. And I'm going to paste, so I do that with a right click. I'm going to paste where that location was. So this is going to move me directly to my downloads, where my downloads are. Okay. And just like before, you see how we have the H2O here. We're going to do the same thing. We're going to do CD H2O dot, dash 3 dot. And here's a trick. You can hit tab and it will autocomplete for you. So we're changing directory into the H2O subdirectory where all my stuff is. So if you would, go ahead and give me a green check again if you are here. Give me a green check. Okay, we'll go through the steps again real quickly. Remember, you do a right click on your start and you click on command prompt. So here, I'll move my screen down here so you can see it. So you do a right click on start, do a left click on command prompt. That will open up this terminal window for you. And we're going to do and actually, if you might be in the right place where you could just do a CD, capital DOWNLOADS. This will work for some of you. CD downloads, and it should move you to the right place. Okay. Give me a green check if you are now here where downloads are. Give me a red check if you need to have some extra assistance, or a red X if you need some extra assistance. Okay, excellent. So what we're going to do is we're going to do CD H2O, and then we're just going to hit tab. And it's going to figure out that we need to change the directory to the H2O subdirectory. We're going to hit enter. Okay. Now we're going to do ls to take a look at all the files in here. Oh, sorry, dir for where we are. And you can see it lists all the different things here. And it looks like we're ready to go. So now here's we're going to check to see if you already have Java installed and the right version of Java installed. So recall that here we had instructions here, and it said go ahead and give this command Java. I'm going to make it a little bit bigger so you can see it. It said Java space dash jar space H2O.jar. So I'm just going to copy that one line, and I'm going to go to this command prompt where I'm actually in that subdirectory, and I'm going to right click to I'm going to paste what I just copied here. So I'm going to copy, Control C, and then I'm going to paste into this command. If you have Java installed, it'll take it a moment, but then it'll start spinning up all those different things. So if you would, go ahead and give me a green check if it started to spin up all of these things. Give me a red X if it said, hey, wrong version of Java, or Java not installed, something along those lines. Okay. Very mixed. I'm not surprised at all. Let's go ahead and figure out how to install Java real quickly. Okay, so to install Java, let's go ahead and go to our, so I'm going back to my, GitHub repository here, just so I can get to the links. We have the section called Installing Java. So some of you might have the latest version, Java 16, in which case you got a different kind of an error. Okay. If that's the case, then don't worry, you may not want to downgrade your Java, but you can if you want to read the instructions here. But most of you don't have Java installed in the first place. So what we want to do is there's this link which goes to the old version, an older version of Java. What happened was they changed the licensing on Java 16. And so essentially it's not as free. You can't pass it around. So you can't use it for stuff like this anymore, which is a real bummer. So we're going to click on this one right here. It's called Java SE 15. We're going to click on that. You might have to sign in at this point. If you do, go ahead and take a moment to do that. And what you're going to want to do is to download the one that's appropriate for you. So it could be the Mac installer, or it could be the Windows 64 installer. And which one did you get? Did you get this one, Umang, or did you just go down to the SE development kit?
I just got the first one.
Okay, yeah. First one will definitely do it. It has some extra stuff in there, but that's not terrible. You'll click on that and you'll follow the instructions. So I'm going to let you follow the instructions, okay, to download, and we're going to continue our conversation a little bit. But I'm just going to be talking you through what the problem is first, while you install Java. So let's talk about our problem here. So we have a researcher by the name of Marcus Eberl, and he works with Stone Age societies from the Mayan civilization. And so he's mapped out a whole bunch of different cities, towns that existed in the Mayan civilization. You know, a lot of these places, there's nothing left except maybe, you know, some parts of buildings or things like that. And it's known that they were a Stone Age civilization, meaning that they built all of their tools, that they built their important tools using stone knapping, which means you would take you're gonna take a piece of rock, you're gonna take another piece of rock, and you're gonna chisel on it until you make it sharp, until you make it the shape that you need it in order to do your work. But the question was, where exactly did these stone knappers work? Because it was a trade. This was not something that everyone knew how to do. I mean, everyone can bang one rock against another, but not everyone can make a really nice sharp rock or arrowhead or tip of a spear, whatever you would need. So these were stone knappers, but where did they practice their trade? Where in the house did they work? And was there a center where they would work? Well, you know, they're not stone tools lying around anymore. Sometimes you get lucky, you run across something like an arrowhead that gets left behind. But there were a lot of tools there. And it turns out there was a lot of leavings from creating the stone tools. You can imagine as you're banging and creating this, pieces are chipping off. Well, when pieces chip off, they're really sharp. And so if you have a small piece, you know, if you have a small piece, you want to be sure that you pick it up because your children could come walking by or other kids can come walking by, and it's going to absolutely, you know, cut their feet. But it wasn't just big pieces left behind. There were tiny pieces left behind, like 4 millimeter size pieces. So very small pieces that would sink into the dirt. You can't pick these up. They're about the same size as a particle of dirt. But in some cases, those are the only things left behind. And these are called lithic microdebitage. Marcus Eberl had an idea decades ago to go and actually take soil samples and look at all these soil particles under a microscope to see if he could find individual pieces of lithic microdebitage. And he did. There are only like maybe 100, 200 pieces of lithic microdebitage in a really rich area out of a 500,000 or million pieces of dirt. So this was really extensive work to even find one piece of microdebitage. But he had a brainstorm really just a few years ago, and it occurred to him he could use industrial 3D particle analyzers. Now, normally these things are used in industry. And what you do is you take your sample of your beads, your little particles that you're creating for some industrial purpose, you pour it into that funnel, and there's a very high-speed camera that's taking pictures as those pieces are falling and tumbling. So you can actually analyze them and take lots of measurements. What's the volume? How round is it? How see-through is it? You know, all the like 40 different measurements it'll take of every individual particle as it's falling through. And then you can determine whether your industrial process is making beads that are perfectly symmetrical or symmetrical enough for your process. What he realized was that he could pour his particles through that, and then maybe he could actually use that to determine whether something, you know, differentiate whether the thing he was looking at was lithic microdebitage, the leavings from these Stone Age stone knappers, or dirt. So there were 40 different measurements, and he was trying to figure out if you could use those measurements to differentiate between the two. And he wrote an article about this, which was just recently published. But what he did at the time was he did a statistical analysis. So is it possible to tell the difference? And he proved, yes, it's possible to tell the difference. But what he didn't have yet was a process that he could run and have, say, particle number 335 is lithic microdebitage, 336, dirt, 337, dirt. Instead, he proved that it could be done using statistics, but statistics generally doesn't give you a way or a model to do predictions. That's not really what it's built for. That's what machine learning is for. So he came to us and asked us if it would be possible to train something that, that could do that. So he had another really good idea. And the other really good idea was that he could get really good samples of stone knapping debris left over, because there are modern day stone knappers. So this is a person who actually can create Stone Age tools using two pieces of rock. And so he's actually striking those. And you'll notice that he's working on top of a tarp. They're collecting all those pieces of lithic microdebitage. So now you have like a pure sample of lithic microdebitage, and if you have a pure sample of, or pretty pure sample of dirt. And you can run both of these through a particle analyzer. So now you have this big old data set with tens or hundreds of thousands of different particles of dirt and tens or hundreds of thousands of particles of lithic microdebitage, each with their own measurements. So let me go ahead and ask you about this. If I were to ask you to come up with a way to differentiate this, okay, right? So I'm going to give you all this data, and let's actually take a look and see what this data looks like, okay? So I'm going to show you the data. I'm going to ask you to think about how you might differentiate between dirt and lithic microdebitage. Here's a link to the data. It's also in that repo, but here's a link to the data. You can click on it. Go and click on ancient artifacts. You can actually look at it in here. So here, if the data is from site, so this is actually one of the sites that I showed you. It says site. And if it's lithic microdebitage, it's called experiment, EXP. This means it was experimentally derived. And then here are all the different measures that it takes. So you can keep on going across here and see all the different measures. Matter of fact, you can even see all the different types of measurements that you can get out of this by clicking on this one that says Ancient Artifacts Variable Descriptions. And this will describe all the 40 different types of measurements that it takes. Ellipticity, angularity, rectangularity, compactness. So these are all the different measures that it can take. So I'd like to open up some breakout rooms and for us to take about 10 minutes to think about how you could differentiate between these two. Here's the deal. I'm going to lock you into a room. I'm going to lock you in a room that has unlimited whiteboard space. And you have unlimited markers, any color you want, right? So you can do whatever you want to on the whiteboards. Unlimited markers, they're odorless because I'm not a monster. And what I want you to do is to think about how you could take this data that we're looking at right here and how you might come up with a way to differentiate between the two. So I'm going to give you all this data that's labeled, but then what I'm going to do is I'm going to give you other data that's not labeled. And I want you to make your best possible guess about whether it is lithic microdebitage, in other words, EXP, experimentally derived, or whether it's soil from a site, which is just labeled site. So does everyone understand that? All right, then I have a link to a working document that we're gonna use in our breakout room. And let's see here. It is right here. Let me go ahead and, oops, no, it's right here. Copy link address. I'm going to go and put this in the chat. I'm going to go ahead and open up the breakout rooms. I'm going to go and reassign the breakout rooms, and I'm going to move you in there. Let's take 5 minutes to do this, and we're going to take 5 minutes to do this, and you can pop out whenever you're ready. Give me just a moment. So we're going to do 5 minutes, and you'll get a 30-second countdown. And let's see. Okay. And one moment. Okay, you all ready? I'm gonna open up the rooms, 5 minutes. Welcome back, everybody. I can tell you all having good conversations because I was watching the breakout room document. It was like blank, blank, blank until like the timer went off and it was like, writing, writing, writing. So let's start with room 2. So who'd like to speak to the ideas that you had?
I can. So we basically kind of started looking at the numbers that were staring us in the face and realized each of them were like, a different, I guess, feature for each of the particles that were examined. So we're trying to see, if there's similarities between the feature values between all the site ones and all the experimental ones, and kind of getting at, what is the average and compare the averages of site and experimental, or, try, because there's so many variables, consider ratios of different features and compare those instead of comparing each feature one at a time to kind of speed it up.
Good.
But
Great.
seems like
Okay.
a good
So
place to use machine learning.
if you can sort of, see if you could sort of find some differences. If you took the average for a particular value, like the sphericity or ellipticity, that's one of my favorite ones. Are there different average values for ellipticity, something along those lines? But great. How about room 1? What are you thinking?
That was the room I was in. Our idea was basically to just write down all the information we have on all of these whiteboards. We have infinite markers, we have infinite space. So just write down everything we have, separate it by whether it's stone or dirt. And then when we get a new particle, we check to see which one our new particle's characteristics match up the best with.
Excellent. Okay, very, very good. Love it. Room 3.
I think that was my room. And there were really great ideas in that room around how you could look at the different variables and start creating groups based on the different variables. So someone said that, maybe you could do a group by on some of the individual parameters, and then, split things based on specific values. And then from those subgroups, maybe change a different variable. If you have information on the location, maybe use that as well. Just this iterative kind of splitting and grouping.
I love it. I love it. So room 1, you have discovered a machine learning technique called nearest neighbors. Because your idea was to choose, find the particles and take this new particle and see what it was closest to, what it was most similar to. That's nearest neighbors. That is absolutely a machine learning technique. Only difference is it's written up as an algorithm and it can work much, much faster than you can than on your whiteboard in your room with all your markers. Room 2, you had something which was starting out as a little bit more of a statistical technique. Are there differences between the two? But that could easily go into a number of different techniques. But that's the start of a number of different techniques. Let's go and say that one's closest perhaps to something like regression, where you sort of find the parameters that sort of define one versus the other. In this case, though, we'd have to do something special with that, something called logistic regression, which is a way to come up with an A or B answer, experiment or site. And room 3, you all have discovered tree-based methods. So this includes a really popular method that's called random forest. So as you can see, machine learning isn't anything which is magical. Machine learning is taking the approaches that kind of seem logical to us, that might occur to us, but doing it in a way where it's keeping track of everything for you. It's exploring all the different things you might do. You can imagine room 3, all the different trees you're gonna have to come up with. Well, maybe it's if the F width is less than 0.1, 0.2, 0.3. Maybe it's not F width at all. Maybe it's the other one. There's a lot of exploring to do. Computers do that extremely well. Let's see how to do this using our new tool. So we're going to need to go through a couple of steps here. So when we last left it, I'm going to go ahead and I'm going to stop this and then I'm going to restart it if I can. Okay, great. So remember that what we did was we're in the subdirectory. See that we're in the subdirectory where we're downloads and we're H2O-3.32. And we're going to give that command that we're pasting in here, which is java space -jar space H2O.jar. If you're not able to get this to run, don't worry. Okay, we have this recorded, you'll be able to go back and do this. We're just looking for a couple of people to do this so you can run this on your own in your room. So if you're not caught up yet, don't worry. So I'm going to run this now. And it's going to start all this up. If I've installed Java and if I'm ready to go, it'll start running. And then you'll notice this interesting little thing right here where it says, open H2O Flow in your web browser. So I'm going to literally copy and paste this address at http://192.168.0.1041. That's also home. I'm going to copy that. I'm going to go to a web browser. And I'm going to paste it in. And this is H2O Flow. So think about the steps that you might want to take here. We need to import our files. Then we're going to do something to actually test out how well we're doing. We have a lot of data, right? We have tens and thousands, hundreds of thousands of examples of the microdebitage and of the soil. So we want to be able to tell if our model is any good. We want to be able to test it on things it didn't train on. So we're going to split up our data. We're going to take some of the data and we're going to train our models on it. We're going to experiment on it. But some other data we're going to hold out. We're going to hold out that data and we're going to use that to test how well our model actually works on data it has never seen before. Because remember, that's what we want to be able to do. We want our model to be able to work well on data it has never seen before. So let's go ahead and go through the steps of how to do this. And if you're up here, you can follow along. So we're going to click on Import Files. And this is one of the parts that I do not like about this, because you have to find where your data has downloaded. Well, let's download our data and then we're going to find where it is. Okay. So here I'm going to go. So here I'm back at box for ancient artifacts. I'm going to go ahead and click on the more options and I'm going to download. So I'm in box, ancient artifacts, the dot menu, more options, and download. And this is in the repo as well, instructions from the repo. It's going to download it here. And it's going to download to my download subdirectory. So if I do my trick of say show in folder, it's just sitting here in my downloads. And it's going to say ancient _artifacts. And I'm going to do the same trick I did before. And the instructions for doing this in Mac are in the repo. But I'm going to right click on it. And I'm going to say properties. And I'm just going to copy this location. And that location, I know it's teeny tiny, but it says C:/users/Spence JB, that's just my username, /downloads. I'm going to copy that. And then I'm going to go back to my H2O Flow. Go back to my H2O Flow. And I'm going to paste that into the import files. And it's going to try to do an autocomplete for me. I don't want it to do that. So I'm just going to paste C:/users/ my username /downloads. And then I'm going to click the search for files. Okay. Now it has all the different files that I have there. What I really want though, and I'm going to help it find it. I'm going to do a / up here. I know it's called ancient artifacts. So I'm going to start typing it. And I'm going to select ancient. I'm going to search for ancient artifacts. Okay, now here we go. So I did C:/users /Spence JB download /downloads / I started to spell out ancient because I had so many files in downloads. That narrowed it down to this one, ancient artifacts. And DSI folks, especially if you can be following along, because you might need to sort of host a room, so make sure that you're loading up. Okay, go and click here, selected files, and I'm going to do an import. So it's going to ask, it's going to want to parse the files. It means it's going to interpret the files. So I'm going to click parse these files. And it's going to tell me what it's doing. It sees that it's a CSV, which it is. It figured out what the separator was. The first row does contain the column names. And I'm going to allow it, I'm going to keep all the standard options, delete the intermediate file on done. So it's telling us what it's guessing for each of these. And about the only change I'm going to make is where it says ID and image ID. I'm going to click next to these, and these are supposed to be strings. So I'm going to change both of those to strings. Everything else is correct. So everything else is correct. All right. And I can click on next page, and that will show me all the different measures. Look at all those measures: transparency, and curvature, and circularity, and solidity. All these different measurements that that device is measuring for us. Now I'm going to click parse. So really all that's happened at this point is my data has now been loaded up into H2O Flow. That's all that's happened. I haven't actually done any work yet. But remember that part where I said that I want to take my data and I want to hold some data out because I want to train my model, and then I want to see how well this model is going to do on stuff it's never seen before. Well, to do that, I'm going to go up here to data. I'm going to click on data, and I'm going to go to split frame. So it's data and then split frame. Data and split frame. So I need to tell it what I'm starting with. I'm starting with this thing called ancient artifacts.hex. And I'm going to split up into these two different things. I'm going to call it, I'm going to call this train, just so it's clear. I'm going to call this one train underscore frame. And I'm going to call this one validate underscore frame. So train and validate, just so it's clear what the role of these two things are. This means 75% of the data I'm going to train on, 25% of the data I'm going to hold out. Make sense? Okay. I'm going to go ahead and create that. So now I have two frames. So questions so far about where I am. Now we're going to do the real stuff. I want to create a model. I want to train a model. And remember, you all already came up with 3 different kinds of models. You came up with a nearest neighbor model, you came up with a regression model, and you came up with a tree-based model. So we're going to explore those. I'm going to start with a tree-based model, or something that uses trees, called random forest. It's fast, it's pretty accurate, so we're going to, well, that's not as much fun. Let's do regression first. Let's do regression first, okay? So I'm going to go here to do model. Look at all these different things. The ones we're interested in that we can do quickly are what's called distributed random forest. There's another tree-based one called gradient boosting. There's another one called generalized linear modeling. And I don't think they have a nearest neighbors one. Charo, do you know if they have a nearest neighbor one? I don't think they do. I don't know. Yeah, I don't think they do. It's not as widely used. Nearest neighbors is not as widely used. It's pretty computationally intensive. Okay, so we're going to do this thing called generalized linear modeling. So this is room 1's. This is room 2's idea. Generalized linear modeling. This is building a model. So this is going to be an automated way for this to automatically train up the model in pretty much the same way that room 2 was thinking. You look at all the numbers, you figure out how the numbers differ between the EXP, the experimentally derived, the modern day stone napper made, versus the site, what came from the soil. So the training frame is going to be train frame. The validation frame is going to be validation frame. What we're doing here is we're telling the algorithm where to get the data from. And validation is the idea of the validation. That's the data that's going to be held out, that it's going to test out on. The response column, this means what are you trying to predict? Well, we're trying to predict whether it was EXP or, what was the other one? We had EXP, what was the other label?
Site.
Site, right. And what did site mean?
It was like collected from the location.
Yeah, that's right. So it was actually scooped up. So that was actually scooped up, where that Mayan city was and run through the analyzer. That's where that site came from. And the EXP came from scooping up the leavings from that modern day stone napper and running that through the analyzer. So we want to predict whether something came from EXP, was EXP or was site. Okay. You only want to use things that are useful, and we don't want to cheat. Because here's a secret. Machine learning algorithms will absolutely cheat given the chance. So if you put in a predictor there that allows it to clearly differentiate, even though it shouldn't be using it, like ID, because if you think about it, these were run 2 different times, right? So maybe the IDs are cumulative. So it might say, hey, if the ID is over 1 million, it's the XP. I know that because that got run second. That's not what we want. We want it to make predictions only based on the characteristics of the particles. So what we're going to do is we're going to ignore some columns. We're going to ignore ID, and we're going to ignore image ID. We don't want any cheating. And then pretty much we're going to let there are all these parameters. We're going to let the parameters ride. We're just going to let H2O do what it does best, which is choose some good parameters for us. The nice thing is there's really good documentation. This is one of the nicest things about H2O. It has excellent documentation on how the different things work. And you can dive into this on your own as you wish. So we're just going to keep scrolling down. We're going to leave all these things as is. And we're going to let it go. We're going to say build model. All right, so we're going to say build model. And it's done. There were hundreds of thousands of data points, but it's already done. This software is fast. So it's done. We're going to view. It'd be really nice to know how well it did. So we're going to view here, and we're going to examine the model. All sorts of different types of graphs here of different ways that it can solve problems. So we'll come back to those in a moment. First question is, what are the most useful different types of parameters? Remember when we looked at ancient artifacts? When we looked at the micro track, so you might have looked at this. So what's most important? If you wanted to tell the difference between the two, all the rooms were saying, well, we have to try out all these different factors, all these different predictors, because we don't know which one is important. Is it ellipse ratio? Is it ellipticity? Is it angularity? What else do we have here? We have all these different types of things that are defined here. And one of the things that's defined is transparency. How see-through is it? Let's go back and see what H2O is telling us. These are the most important predictors. They're in order by their importance. This is the most important predictor was transparency. And based on the coding, I know that the more transparent something is, the more likely it was from the experiment from that stone napper. So this is lithic microdebitage. Why do you suppose that's true? Any ideas on why transparency might be important? What story does that tell us? Let's think about what's happening here. We're taking a piece of stone and we're chipping off pieces. Are the pieces like round, thick things? What are we trying to make here with the stone tool? Are we trying to make something round, or are we trying to make something of a different shape? Yeah, they're kind of shavings, right? And the whole idea is that we're getting stuff that's really sharp. Ah, Jeffrey, absolutely. This could be obsidian. Even if it's anything which is going to break like that, is probably going to be something that's like obsidian or something which is crystalline. It's going to, the whole idea is that it creates these really sharp edges, right? So the leavings are kind of probably be really sharp, really thin. This is exactly what the machine learning algorithm came up with. And this is one of the uses of machine learning algorithms, is to understand what's happening with the data. So when we ran this the first time earlier this year with Professor Eberl, Sharo, do you remember his expression when we ran this for the first time? He said, yes, yes, because it had discovered that transparency was important, really important. And sphericity, it's important in the other direction. The more spherical something is, the less likely it is to be leavings from making stone tools. So this is called a predictor importance. That's what this is. And it tells a story all on its own. So, but how well is the model doing? Well, we do have a way of judging how well a model is doing. We don't have time going into exactly what this is right now, but come for a later workshop in the fall, and we'll cover this more in depth. This is called the area under the curve. This red line means that your model is at chance. This curve means that it's doing much better than chance. And ideally, a perfect model would be almost like a right curve here. So we want this to be almost 1 here. So the higher it goes, the closer to 1, the better the model is. The better the model is at differentiating between experiment and sight, and the fewer mistakes it's going to make. It's going to make fewer confusions, and it's going to get more things right. It's a balance of all those things together. So the number to beat is 0.89. We want a model that does better than 0.89. So what we're going to do now is we're going to break out into rooms again. We're going to take about 10 minutes. And I'm going to put some DSI folks in each of the rooms and just put other people randomly in there. And you're going to try to run on your own. If you can't, then you can just give some guidance to the DSI folks in the room. I'm going to go ahead and create those rooms right now. And let's see. So Umang, I'm going to put you in that first room again. And I'd like for you to in your room, go ahead and see if you can do anything to get a better model using random forest. Okay. And I might just break folks up into to 2 rooms. Well, no, we'll do 3. Okay. Okay, for room 2, Preston, I'm going to put you in this room. If you're okay, if you can go ahead and see if you can do something with gradient boosting. Okay, and Charo, we have the linear model, the general linear model left, right? Is there anything else that you would want to try other than general linear model? Okay, then I'm going to go ahead and set these rooms for 10 minutes. So the idea here is Go ahead and make suggestions, explore what parameters you might be able to change, see how well your model might run with just the basic settings, see what you can do to maybe improve some of these. So for Sharo, for example, you might want to explore some interactions, right? So we'll see. All right, I'm going to open up the rooms. You'll have 10 minutes. We're going to come back and be sure to have somebody report out how you did. All right, I'm opening the rooms now. Have fun. And Preston, are you still here? You crashed? Welcome back, everybody. Welcome back. All right. Charles, let's start with your group. You all were using regression. And how did you improve your model? And what was your score?
So those are great questions. We were kind of struggling a little bit just to get the models together and have things running on our computers with Zoom. But we were able to do the interactions, and we kind of studied the coefficients to see how strongly the interactions were really making a difference there, or whether they were seeming to be worth including, which was really interesting. And so what we interacted was, what was it again? And so I think it was roundness and transparency, or like compactness and transparency. So we could understand kind of that relationship. But because it kind of showed up a little bit more towards the bottom. Zoe might be able to, she might be able to tell us more about the performance. Yes, thank you. She was running it. But it was very interesting to see. Does anyone else want to say anything about that? It was cool experience. All right.
So, and do you remember what your AUC was on your validation metric?
Zoe, do you happen to have that one? She's constrained by technology for the moment, as are all at this point. go. She's saying 0.87.
0.87, okay, great. So 0.87, we'll keep that in mind, 0.87. All right. Let's see if that made its way into the breakout room. So breakout room 3, you got to, oh, okay. Oh, I see you. It's right there. Okay, great. So you got 0.87, perfect. All right. Room 1. You all were doing random forest, is that correct? Excellent. Tell us a little bit about that.
All right, so we first spent a little bit of time really understanding what random forest is doing compared to what we just talked about. So we spent some time looking at that and then kind of just ran the default random forest, and that gave us an AUC of 0.93. And then we talked about, the parameters that we can change, and we changed the tree depth and the number of trees, and that got us to 0.945.
Okay. So you changed tree depth. And what was the other one?
And the number of trees.
Okay. And you got to validation 0.94, you said?
Yeah, 945.
945.
Yeah.
Okay, great. Excellent. All right. Adrian, would you mind talking a little bit about our room, what we did?
Okay, so we made a model from gradient boosting. So what boosting does, you want me to explain what boosting does?
Oh, just in one sentence, if you could, just tree-based method, right?
Yeah, so it starts off with one model, and then the subsequent models are improvements upon the previous model to improve the prediction accuracy. And we create a specified number of models, and the prediction of the last model that we construct is going to be the prediction that we use to predict whether this particle is just dirt or the crystalline thing, the
Excellent.
lithiums.
And do you remember what the first validation, or does anyone remember what the first validation AUC was? I think it was like 0.95. It's already not doing too bad. But then, Adrian, you had an idea of some parameters to change. What parameters did we change?
We changed the number of trees to construct, because if you construct more trees, then you'll get more predictive power.
Yes, exactly. And so our validation, so first of all, what happened to our training set? How well did we do on our training set?
The training set, it predicted very well, like 0.95 or something.
Yeah, and actually when we bumped it up to 250 trees, it was like 0.78 something, 0.978. Really good, right?
Mm-hmm.
But what happened to our validation set?
So validation, I think at first the validation set, it had a test accuracy of 0.89, I think, and then when we bumped it up, it was like 0.95, and then again it was 0.98.
Yeah, 0.95. It was 0.958. I think was the very last one.
0.955 and then 0.958. Yes.
Yeah, exactly.
So, and the first one was like 0.898, 0.899.
So in short, what happened was we did see an increase in the validation AUC here, and I'll just share my screen with all the numbers here. So we saw an increase when we increased the number of trees. We saw a great increase in the training, but only some of an increase in the validation set. This is an example of what's called overfitting. These models are very, very powerful, and you can think of it along the lines of the model starts to get on a first name basis with each of the particles, the data for each of the particles. And so it begins to create specific rules for each individual particle, because it can, but it has enough trees, it can start doing that. But that doesn't generalize too well, because it's finding properties that really don't matter that much. So even though the training AUC went up, our validation AUC went up, so we're going to keep that model. So we got 0.958, still pretty good. And actually, it looks like out of all of these models, this was the best performing model. So Dr. Bell and Umang and Preston, let me ask you all, does this mean that we should always use gradient boosting?
Of
No.
course not. Gradient boosting is just one of many different methods you could use.
Excellent. And there is no way to know before you solve a problem which of these models is going to perform best. Those of you who've used general linear models before, what's one reason you might want to use a linear regression model, for example, even if it's not as well performing? Charles, I know sometimes you have preferred a linear regression model. Why might you prefer one?
So with linear regression, something that I like is that it is kind of it tends to be a really nice model a lot of the time. So even if you have really, really complex data, it can be really straightforward, fast to compute, and give pretty good performance as well. Also, if your data happens to hold to some statistical properties, you can make some conclusions off of that. But that's a really strong if. But it can be a really nice model. And I think also it offers a lot of interpretability. Like, so when we were looking at the coefficients, you look at the coefficients and they give you very clear insight into what the model thinks is important. So they're just some of my thoughts.
Nice. There are a bunch of different methods that we didn't try. Neural nets, we didn't try that. The nearest neighbor ones, we weren't able to try that one out. So part of this cycle of doing the modeling and testing and assessing how well a model is going to be working is exploring different types of algorithms, attempting to try out different parameters. Matter of fact, there's something called AutoML that H2 offers that people love, that will actually go through and try a number of different parameters and search that parameter space for you to find things that maximize that validation of performance. But remember, all of this is just in a small part of what is a larger data science project. But I gotta admit, I do love this part because these are amazingly powerful models. You're able to do work here that was simply, we did work here right now that was simply not feasible. Certainly 20 years ago, even 10 years ago, this would have been kind of hard to do because it's a fair amount of data. And so it would take a while to crank through this. Now we can do it in a matter of minutes, we can do it interactively, and we can actually, in a single setting, provide a tool, a predictive model that can reshape someone's entire research and actually reshape, in a real sense, the world of archaeology, because now you have a brand new kind of an approach. You want to figure out what's been going on at a particular site, take a soil sample, run it through a particle analyzer, and use Professor Eberl's trained machine learning algorithm, and it will tell you what's dirt and what is the leavings of Stone Age artisans. We're at the end of our time. I'll stick around and answer any questions that people might have for a few minutes. And Adrian or Laura, if you'd like to stick around, I can make you host as well if you want to stick around longer.
I can stick around.
Okay, great. I will make you host then.
Okay, thank you.
Thank you, everybody. Good to see everybody. And remember, we'll have the recording
Also,
shortly.
Jesse, it seems like you haven't uploaded any of the prior workshop recordings after the Streamlit workshop.
Ooh, I may not have made those public. Thank you very much. I will check on those when I upload this recording tonight. Thanks for letting me know.
You're welcome.
All right, everybody. See you soon.
See ya.
Bye.
See ya.
Bye.
So does anybody have any questions about this stuff?
Agent, first off, do you have the
Yes.
recording off right now?
What?
Is the recording still going?
It appears the recording is still going.
Here, I can turn it off.